Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about projections of the oblique lines. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. An oblique line is the one which happens to be inclined to both the reference planes, that is horizontal plane, as well as the vertical plane. Now, since an oblique line is inclined to both HP and VP, neither of the front view or the top view, they will be parallel to the reference line, and the projections of the line on the horizontal plane and the vertical plane will reveal the apparent length of the line. And we are not going to obtain the true length of the line in the front view and the top view. So in order to obtain the true length of the line, we need to use the principles of rotation of the line method to evaluate the true length of the line in the front view as well as in the top view and their inclinations with HP and VP. Now here we have been provided with the physical real world environment situation which needs to be converted into the orthographic projections of the oblique lines, and then using the principles of the rotation of the line method we will be able to obtain the true length of the line. So here into this situation we have been provided with a room which is having the dimensions 5 meter, it is the width of the room, 4 meter, it is the depth of the room, and 3 meter, it is the height of the room. So here we have got a room having the dimensions 5 meter width, 4 meter depth and 3 meter height. It has got a fan suspended from the center of the ceiling and 0.5 meter below the ceiling. So here we need to obtain first of all the center of the ceiling. So here we have got, this is the floor of the room, this is the ceiling of the room, and these are the 4 walls of the room. Now into the ceiling we need to join the 2 diagonals of the ceiling and we will be able to obtain the center point of this particular ceiling of the room. So from this ceiling 0.5 meter from the top we have to suspend a fan over here. So this is the location of the fan, and this location of the fan happens to be 0.5 meter from the ceiling. So it is the center of the ceiling which we have located, and from this particular center 0.5 meter from the top, this is the location of the fan. And once we have installed the fan over here, this fan, it is connected to a switch which is located in one of the corners of this particular room, and this switch is located at a height of 1.4 meter from the floor. So this is the location of the switch. So if a switch, it is located at one of the corners of the room at a height of 1.4 meter. Now we have to join this point which is going to represent the location of the fan, and we have to join this point with the location of the switch over here. So this is point 1 which is called point A, which corresponds to the location of the switch. And once I join this line AB over here, that is joining point A which corresponds to the location of the switch and point B which corresponds to the location of the ceiling fan which has been suspended 0.5 meter below the ceiling over here, and it is located centrally into the ceiling of this particular room. So we are required to evaluate the length of this electric wire or this electric cable using the principles of the orthographic projections. And once we draw the orthographic projections of this room, we'll be able to convert this real life problem into the projections of the oblique line problem. That is, the front view of this line A dash B dash and the top view of this line AB will be drawn into the orthographic projections, and then using the method of rotation of the line we'll be able to obtain the true length of this electric cable which is going to join this switch A with the ceiling fan which is located at point number B over here. So here, in order to draw the orthographic projections, we need to evaluate the front view as well as the top view of this room. So the scale which we are going to use over here, it is 1:100. That is, reducing scale will be used over here. So 1 meter will be represented by 10 millimeter over here, right? So here we have got the width of this room which is equal to 5 meter. So into the orthographic projections, this width of the room which is equal to 5 meter will be represented as 50 millimeter using a scale of 1/100. Similarly, the depth of the room which happens to be 4 meter will be represented as 40 millimeter into the orthographic projection. And finally, the height of the room which happens to be 3 meter over here will be represented as 30 millimeter into the orthographic projection. Now, when we have to draw the orthographic projections, we have to draw the front view of this room and the top view of this room. So into the front view, the two dimensions which will be visible to us, it will be width which is equal to 5 meter, that is 50 millimeter, and the height which is equal to 3 meter, and this will be drawn as 30 millimeter into the orthographic projection. So the front view of the room will be represented with the help of a rectangle which will be measuring 50 millimeter by 30 millimeter. Similarly, into the top view orthographic projections, we are going to view the width of this room and the depth of this room. So width of this room happens to be 5 meter. So the distance which will be marked in the orthographic projections will be 50 millimeter corresponding to the width of 5 meter, and by 40 millimeter, that is corresponding to the depth of the room equal to 4 meter. So the rectangular construction of 50 millimeter by 40 millimeter will be representing the top view construction of this particular room. And with this information, we are required to draw the projections of the line in the front view, that is A dash, B dash, projection of this line in the top view, that is AB. We are also required to evaluate true length of this line AB using the principles of rotation of the line method, and we will be evaluating the inclinations of the true length of the line with respect to horizontal plane and the vertical plane, that is angles theta and phi will also be evaluated. So this is the 3D representation. We can see this is one of the corners of the room which we have got, and at a height of 1.4 meter into one of the corners we have got the location of the switch. So this is the location of the switch that we have got, and into the center of the ceiling 0.5 meter from the top. So ceiling fan has been mounted over here, and this ceiling fan has been directly connected with this switch which is lying in one of the corners of this particular room with the help of an electric cable or an electric wire. So we need to evaluate the distance between these 2 points, A which represents the switch and B which represents the location of the ceiling fan. So in the 3D also you can check, this is location of point A, this is location of point A, and this is location of point B. So the length of this electric cable as well as its inclinations with HP and VP need to be evaluated. Now let us start with the construction of the orthographic projections of this particular room. So we know that the front view of this room will be represented with the help of a rectangle which measures width 50 millimeter and height which is equal to 30 millimeter. So the width of the room we have marked as 50 millimeter over here, and the height of the room we have marked as 30 millimeter over here, right? So this is the front view orthographic projection construction corresponding to this particular room. Similarly, we can draw the top view orthographic construction. So here we have got, for corresponding to the top view, width remains as 5 meter, that is 50 millimeter. So this is the width of the room which we have already marked in the front view, and the depth of this room happens to be 4 meter, that is 40 millimeter will be the rectangle depth over here. So 50 millimeter by 40 millimeter, this completes the construction of the top view projection of this particular room. Now, first of all, we have to locate point B over here. Why? Because it is located centrally at the ceiling over here. So first of all, we have to locate the center of the ceiling. So in order to locate the center of the ceiling, we need to obtain the diagonals. That is, the two diagonals we need to join. The moment we join these two diagonals, the center point of the ceiling we have been able to obtain over here. Now, we can check that this is the location of the point A, which lies into one of the corners of the room. This is the location of the point B. This is location of the point B, which is lying 0.5 meter below the ceiling over here. Now, this point B, when we are going to look from the top, this point B will be projected at the center over here. It will be projected at the center of the ceiling. Similarly, this point A, it lies into the leftmost bottom corner over here. So this point A, when we are going to look at this point A, irrespective of this height, this point A will be projected into this corner. So it means that point small a will be located here, point small b will be located over here. So point A will be located into this corner and point B will be located at this particular position over here. So point A and point B, once we locate both of these 2 points, so we can join point A with point B. So it means that corresponding to this true length, I have been able to obtain the apparent length projection of this cable, which is going to join this switch with this fan over here, right? So the top view projections of this line AB, they have been obtained in the orthographic top view projections into this situation. Now, having located this point B, now what we can do, we have to draw a horizontal locus line through the point A and horizontal locus line through the point B, because ultimately we will be using the principles of rotation of the line. So obviously, in order to obtain the rotation, the locus lines, they have to be drawn first of all. So point A and point B, that is the apparent length projection of this cable or a string, has been obtained in the top view. Now let us look at this particular string in the front view. So when we are going to look at the string from the front view, one thing is quite apparent. Wherever we have obtained point A, onto this vertical locus line, I will be able to obtain the location of the point A dash. Similarly, wherever I have been able to locate the position of the point B, onto this vertical line, the location of the point B dash will be obtained over here. So A dash will be obtained into this vertical locus line orientation and B dash will be located alongside this particular vertical projector line over here. Now when we are going to look at this particular room from the front side, so we see that this cable which is joining this particular switch with this fan, so point A will be located into this corner 1.4 meter above this floor or the ground. So we have marked this distance 1.4 meter above the floor or above the ground. So we draw a horizontal locus line over here, and this is the location of our point small a dash. So small a dash will be located over here. And what is the location of small b dash? That is the front view corresponding to the point B. So this is my center point. You can see this is the location of the center of this room. But this fan has been mounted 0.5 meter from the ceiling, that is below the ceiling. So from the top of the ceiling, I mark a distance of 0.5 meter. So 0.5 meter means that I mark a distance of 5 millimeter from the top. The moment I mark this distance 5 millimeter from the top of the ceiling, this gives me the location of the point B dash. So B dash means that it is giving me or providing me with the front view location of the ceiling fan over here. So this will be the location of point B dash. This will be the location of point A dash, because point A dash lies in one of the corners of this particular room. So A dash is obtained over here, this point. B dash, it is obtained over here. So the moment I obtain these 2 points, A dash and B dash, so I have been able to obtain the front view projections or the apparent length projections corresponding to this cable. So the points A dash, B dash, that is the front view projections, have been obtained. Points A, B, that is the top view projections corresponding to this cable AB, they have also been obtained in the top view. Now we have to use the principles of rotation of the line in order to obtain the true length of this particular cable which is going to join this fan with this switch. So in order to obtain the true length of this line in the plan, so we know that the front view apparent length projection must remain parallel to the horizontal plane, which it is not in this particular case. So this projection A dash, B dash, it does not happen to be parallel to the horizontal plane. So what we need to do, as per the principles of rotation of the line method, A dash will be my needle point. I'll open the compass equal to the distance A dash, B dash. With my compass needle located at A dash, I'll open compass equal to distance A dash, B dash and draw an arc which will be extended up to the locus line of the point A dash, such that this distance A dash, B dash should be transferred over here, and this point B1 dash which has been obtained, A dash, B1 dash, this is the apparent length projection in the front view which has become parallel to the horizontal plane. So the moment I have been able to transfer this apparent length projection in the elevation parallel to the horizontal plane, now from this point B1 dash or from this point B dash over here, if I draw a vertical projector up to the locus line corresponding to the point B over here, I will be able to obtain the true length of this line in the top view. I will be able to obtain the true length of this line in the top view. So what I am going to do, having rotated this apparent length with respect to this particular point A dash locus line and made it parallel to the horizontal plane, so through this point B1 dash, I am going to draw a vertical projector and extend it up to the locus line of the point B. And the moment I extend this vertical projector up to the locus line of the point B corresponding to this point B1 dash, I will be able to obtain point B1, and this point B1 when I join with point A, so I'll be joining these 2 points A and B1 using a blue line which is going to distinguish apparent length which was drawn by using a black line, and these two will be distinguished because this is the apparent length and this one, it is the true length of the line. So AB1 gives me the true length of the electric cable which is going to join the ceiling fan with the switch over here. So once I obtain this true length AB1, so I can evaluate the angles of inclination of the apparent length, that is AB with vertical plane. This will be marked as angle beta, and I can also evaluate the angle of inclination of this true length, that is AB1 with the vertical plane, and this angle of inclination of the true length, that is the blue line, it happens to be angle phi, and we can check that true length, it is bigger than the apparent length, and the apparent angle of inclination beta, it is greater than true angle of inclination phi over here. So here we have been able to evaluate true length of this electric cable in the top view. Now we want to proceed and we want to evaluate the true length of this line in the front view as well. So in order to evaluate the true length of this line in the front view, now once again we are going to use the fundamentals of the rotation of line method. That is, whenever the apparent length of the line in the plan, it happens to be parallel to the vertical plane, on the vertical plane in the front view, we are going to obtain the true length of this particular line AB. So here once again we have got the apparent length of this line, that is AB. It is not parallel to the vertical plane, it is inclined to the vertical plane. So what we are going to do, we are going to rotate this line or the apparent length AB and make it parallel to the vertical plane. So our needle point will be point A, open compass AB, and then through B draw an arc up to the locus line corresponding to the point A, such that AB2, because this is the second rotation, so the numbering of this point will be B2. So AB2, this is the apparent length of the line in the plan. So this is the apparent length projection of the line in the plan. So this happens to be parallel to the vertical plane. So if we draw a vertical perpendicular or projection from this point onto the vertical plane up to the point B dash. So please check, if I draw a vertical projector line starting from point B2 up to the locus line of point B dash. So this point, that is B2 dash, I will be able to obtain. This is the location of the point B2 dash. And the moment I obtain this point B2 dash over here, now I need to join A dash with B2 dash once again using a blue color line, just to distinguish between apparent length A dash B dash, which was drawn with the help of a black color, and A dash B2 dash, which has been drawn with blue color. So blue color line A dash B2 dash happens to be true length. The moment I evaluate this true length, automatically and instantaneously I will be checking A dash B2 dash must be equal to AB1. That is, the two true lengths which I have obtained in the front view as well as in the top view, they should be equal to each other. Only then this solution will be assumed to be correct. Now having obtained this true length, now I am going to evaluate the angles of inclination of the apparent length in elevation and the true length in elevation with respect to the horizontal plane. So A dash B dash, that is the apparent length in elevation, it is inclined with respect to horizontal plane at an angle alpha, while the true length A dash B2 dash, it happens to be inclined with respect to the horizontal plane at an angle theta. So once again we can check the true length of the line in elevation A dash B2 dash, it happens to be greater than the apparent length of the line A dash B dash in the elevation, and the apparent angle of inclination alpha will be greater than the true angle of inclination theta in the front view. So this way we have been able to evaluate the true length of this distance between these 2 points. So point A represents the location of the switch, while the point B represents the location of the ceiling fan. So this true length has been located in the front view as A dash B2 dash, and it has been located in the top view as the distance AB1. And the final check towards correctness of the solution is that A dash B2 dash, that is the front view true length representation, should be equal to top view true length representation. So if both of these true lengths they are equal, it means we have followed the principles of rotation of line in an appropriate manner, and the solution thus obtained is correct over here. So this is all for today. So I hope that through this discussion you would have understood about how you can go about conversion of a real world situation into the projections of the oblique line using the principles of the orthographic projections, and thereafter how we can use the principles of rotation of the line method in order to evaluate true length of the line as well as the true inclinations of the line with respect to the two reference planes HP and VP. So we'll be continuing with further discussion regarding few more cases on the projections of the oblique lines in the coming lectures. So thank you very much. Thanks a lot.